Let's start. First, can everyone hear me all right? Is the audio okay? Okay, thank you. Appreciate it. So I'm asking because I'm going to switch to my iPad pretty soon by sharing screen. And if I do that, I won't be able to see your chat. So the only way, or the encouraged way is to speak into the microphone, okay? Don't worry if you interrupt me. If you have any questions or if I ask questions and you want to answer, just speak into a microphone. But once again, I won't be able to see your chat once I share my iPad. So the first few things I want to go over. All right. So this is like from the previous note I just wrote for my stochastic processes class today, but it won't matter. Just basically a few basic things. So the first thing is please read the syllabus. Those contain the common rules that apply to all students in the summer, coming from the course coordinator. Now, a few things about me and my class that you may want to know before you decide to continue with the course. The first thing is about exams, and basically, I do not provide any practice exams or reviews. Has always been what I do. I am aware that professors these days give so-called practice exams in which you memorize the answers and you would expect to write down those answers for the real exam and get an A. Not going to happen in my class, okay? The only answer I provide to questions of the type like how would you study for the exam is study the lectures and study your homework, okay? On that note, questions like how many questions will be on the exam will not be answered because I don't know until I write them. So practically speaking, don't ask me any questions about the exams. About the grades, same thing. Grades will be provided based on your performance only, meaning that if you expect to have some kind of curve in this class or some kind of extra credit toward the end, if you're not doing very well in the class, won't happen. So there might be curve if every single student in this class does not do well in my exams, which actually I don't think happened. What usually happens is half the class does very well and half the class doesn't do well at all. In which case there's no curve because there are people who does very well in the class. Okay, I'm saying this because I always get some sort of questions that along the line that this is your last semester, you need this class for some other class, blah blah blah. Again, right? It'll be purely based on your performance. 90% A, 80% B, 70% C, 60% D, things like that. You should just gauge your performance based on that breakdown of the curve. Forget about this prerequisite. That's a leftover from my previous class. Yeah, here. This class, even though it's online, is not meant to be one of those online courses where you can just sleep through the lectures and then watch the recordings after or whatever. This is like a synchronous class where you're expected to come to lectures, engage with the materials, and learn from the materials. So basically, just treat it like a regular class, okay? Just conduct it online. So I'm saying this because the lectures are recorded, and under some exceptions, I may provide the recordings, but it's all right through my discretion. And so you should generally expect that if you ask for recordings, it will be denied. So just come to lectures if you well, you have to come to lectures anyway, right? Which exactly is about the point of the attendance quizzes. Every single lecture will have attendance quizzes. Well, what are they? I'm going to give you some example of attendance quizzes in my previous class. So basically, I write down something like this, right? Quiz 1, quiz 2, etc. Right? And I'll give some question, and then I'll give, I don't know, a minute or so for you to think about the question, and then I'll ask if anyone wants to say anything about the question. Basically, the goal, of course, is not for the students to solve the question completely, but for you to engage with materials. In which case, I think it helps, right, with for you to kind of digest the material faster that way. As far as the quiz is concerned, right, after a minute or so, and after I ask the questions, I'll be providing the answers to the question. Your task, right, for the quizzes is to just copy down the question and the answers, all of them, and submit, right, to the assignment on Canvas after the lectures. You have 15 minutes to do so. Now, all you have to do is copy all the questions, to write down all the questions and all the answers. But some students will take notes anyway, right? And I guess that's the whole point, that if you take notes and you upload your notes, that counts, right? You don't have to just like select the questions and answers only. But if you take notes of everything, that's fine, right? That will count as a quiz answers. So again, right, basically, even though I call them attendance quizzes, it's just basically taking notes. And so because of that, right, a lot of time I won't be checking the content of the quizzes. I'll tell you that ahead of time. If there's something submitted, you get full credit. However, okay, this has been abused in the past in many, many ways. I don't care to tell you. Well, maybe I care to tell you. Students would not attend classes and submit something. Students would borrow their friends' notes and then, take a picture or something and upload, whatever, okay? Now, if you're caught cheating even once, and I have ways to check, you will receive 0% in the quiz category. That means 10% off the entire grade of the course. And there's no appealing. I mean, what if I catch you cheating, that's 0%, okay? For your past quizzes and for your future quizzes, meaning you just might as well not even care to take the quizzes. The reason, right, again, is that the quiz are just meant to encourage you to come to the lecture, right? There's no testing, no nothing here. And if you even cheat, then I don't know what to tell you. So the message is, please don't do so, okay? It's just painful for both parties. Beyond that, not much to tell you. If you have any questions, during the lectures regarding math, feel free to interrupt me at any time. I'll be more than happy to clarify any content for you. Okay, so having said that, is there any question before we begin the lecture? Okay, so once again, if there's any issue with the quality of the lecture, you cannot hear me clearly, please just speak to your microphone, because I won't be able to see your chat. So that's 477, intro to probability. So we'll be going over, I don't know, 5 or 6 chapters or so in the text, right? Look at the syllabus. The first 2 chapters, chapter 1 is combinatorics, basic combinatorics. Chapter 2 is axioms of probabilities. All right, so obviously chapter 1 is meant to be covered before chapter 2. However, I think in terms of the flow of ideas and concepts and the course of a probability anyway, I'll say a few things about chapter 2, in particular 2.2, okay? And maybe 2.3, whatever. It's not exactly kind of doesn't have to be really within 2.2. It's called the sample space and events. Before I go back to chapter 1. So I'll say a few things about this first, and then go back to chapter 1. Okay, and then we're gonna do more of chapter 2 later on. The reason is like basically combinatorics is going to be a very important tool in many things, right? Probability included. But if we just do combinatorics, it's sort of like not well motivated on why we want to study combinatorics and what's the connection to probability. So that's why I want to kind of say a few things first and then do combinatorics. So, well, maybe the first question here is, right, what is probability? I'm not sure if that's even a well-phrased question, but let's just throw it out, right? Well, again, I mean, I assume that all of you guys here have heard of the word, right? And maybe have done some, let's say, elementary probability back then in previous courses, whatever. But so I want to say this word maybe in contrast to the other field, which is also very popular this day, is statistics, right? Again, so at Rutgers, right, 477 is probability, 481, right, is mathematical statistics, for example, which has this course as a prerequisite. And I also ask the same question if I teach that class, because I think these two concepts tend to be confused, or maybe people just lump them together in the same category, which I don't think is a good idea. Now, of course, we won't do this here in this class, but basically at this level, assuming you have no idea what probability is, which is fine, you should know, you should keep this in mind. Probability, in my opinion, belongs to the theory side or the modeling side. And statistics belong to the, let's say, empirical verification, data collection, things like that. All right. So basically, in some way, statistics are things you do to verify the theory you develop or the model you develop using probability. All right. Of course, statistics itself has its own theory, so it's not quite clear to say what it means for probability to be theory. But if you take probability to be model, then statistics, right, is empirical. It's about kind of collecting data to verify the model in certain ways. Well, I'm saying this, right, because basically when you do probability, or when you study probability in this class, right, things proceed using axioms and then logic. So axioms, assumptions, logics, right? These are the things we use to develop our probability. And therefore, when you do probability, the one thing you always have to keep in mind is, what are the assumptions? What do I have, right? What can I conclude? Well, let me give you an example I have in mind to demonstrate this. a favorite thing students in probability likes to do is they like to assume events are independent. All right. Now, again, if you don't know what the word independent means, that's fine. But I think some of us here have seen this word before I even know what that means. Let me give you an example. Basically, for example, if someone asks what's the probability that if you toss a coin twice, 2 heads show up, the answer will be easily 1/4. And the answer, the justification for that answer will be that it's going to be the product of, first head, second head, which is 1/2 times 1/2. And I think, right, everyone among you will think that this line of argument is perfectly natural, perfectly fine. There's nothing wrong with that. Well, I can sympathize with that point of view. On the other hand, the big no-no in this line of argument is the assumption that you use when you say that these two events are independent, the first toss and the second toss. It's not that I think, right, I myself think that the first toss and second toss are not independent or whatever. I mean, intuitively. The problem is that we are doing theory. And unless someone tells us or someone make the assumption that the two events are independent, the first toss and second toss, you cannot put that into the problem yourself. Okay? Again, right, these are sort of like a little bit subtle, but the general line of thought is that when you study this course, you should pay attention to these things, all right? And do not make any unwarranted assumption that's not in the problem. Okay, so now, to be more specific, right, what is probability? Probability is a way to assign, right? Let's call the word likelihood because, we already have the word probability that we want to define, right? Two events. All right. Let's say, two events, right? So, for example, I guess I already allude to things here. For example, right? When you toss a coin twice, when we say that right? So first of all, when you toss a coin twice, what can you expect to happen? Well, you can expect 4 things to happen, right? It can be head, heads, tail, tails, head, tail, tail, right? And this will exhaust all possible outcomes. Okay, so I'm introducing keyword here, terminologies here, right? The word outcomes. We'll kind of like say a little more rigorously what that means, but I guess it's sort of like intuitive, right? So this is all possible outcomes, and so this is called the sample space or the universe, right? Denoted by omega. So let's call it the universe or the sample space. Let me check that. That's the word. It's been a while since I used this word, but I just call it the universe. But sample space. Right. So basically, the collection of all possible outcomes, right? I think the textbook denoted by S doesn't matter, right? S omega. So it's basically the collection of all possible outcomes. Now, within this universe, right, within the set of all possible outcomes, what do you want to do? Well, you want to assign, right, likelihood to this, let's say, outcomes. And what that means, right, is you want to assign a number, right? So likelihood now is let's say a number, a value, right, between 0 and 1. right? Where the notation P of E means probability of event E. Okay, so notice, right, there's a word event and there's the word outcome. Okay, now outcome is an event, but an event can be more general than an outcome. Okay, well, we'll clarify that later. But for now, right, we're discussing what is probability. So again, right, basically right now at the basic level, we want to be able to say, for example, what is this? What is this? And so on and so forth, right? So again, the question mark here is meant to be a value between 0 and 1. But, you know, if you're doing math or if you're doing anything logical, right, you cannot just assign values out of nowhere, meaning that there are rules to follow, right? So these are the rules here are basically what the textbook call the axioms of probability, right? I mean, already, right, one of the rules is that the value is between 0 and 1. But, you know, other values that you may already know about, for example, is that, right, whatever the numbers you assign here, let's say this is head tail, right? And this is tail tail, right? So there are 4 numbers to assign, right? But whatever numbers you assign here must add up to 1, right? Because that's the probability of the universe, right? For example, right, 1, right, it's guaranteed that one of the outcome must happen, things like that. So anyway, right now we're not really listing out the essence of probability because, like I said, I just want to discuss enough of this section to go back to chapter 1, right? And we're going to go back to chapter 2 and talk more in depth later on. Right now, I want to draw your attention to the fact that all of these are question mark. Now, I know that you're itching to fill in 1/4, right, for each of these because it all seems so natural. And the remark here is not really. Why do you have to fill in 1/4 here, right? Based on what requirement, based on what law, based on what axioms, right? Because there's no rule for us to follow. So we cannot say that, oh, it's so natural, so we do it that way. So the question is, when you do this, what assumption? I mean, again, right? Filling 1/4 for each of these is not bad. It's just what assumptions are we following when we do so? Okay. And moreover, from these assumptions, is that what consequences or what kind of, you know, if you don't fill in 1/4 and you fill in some other values, right? Like 1/3, 1/3, and then, you know, some other values of 1/6 here. What happens, right? What are you saying? Well, you see, right? First of all, if you just stop at the level where you say that probability, right, is a way to assign likelihood to events, then there's no single way, there's no unique way to assign, let's say, probability to outcomes. Okay. Now, maybe let me right here clarify the difference between outcomes and events for you. And this happens, I think, at the discrete level, more or less. But you can think of outcomes as like the smallest event. All right. For example, right, when you toss a coin twice, so okay, what do we mean by smallest? There's nothing as a subset. There's no sub-event inside it, right? So let me give you an example of what an event is. What are all the events in this experiment when you toss a coin twice? Well, when you toss a coin twice, you can talk about the event E. I mean, E is just a generic name, right? E or F, whatever. which is that the first toss is a head. Okay. Now, this is an event that makes perfect sense, right, within this universe. But clearly, right, this E is not any of these outcomes, right? In fact, right, what is E? E is the union of two events. Sorry, two outcomes, right? Well, an outcome is an event anyway, so it doesn't matter. But yeah, right? So E is a union of these two, right? Because if you have head or head-tail, that's saying that, right, the first toss is a head. Now, of course, right, I mean, this is an overkill, but you can write something like this. That's the union I'm talking about, right? You union these two set, you get this set, right? Which is first toss is head. So here's a place where I want to clarify that when we write something like this, right? This sharp pointy bracket, it just means a set, right? This comma should be read as or when we list our outcomes, okay? Because I think people might read this as and, head, and head-tail. Well, that's when you include things in a set, but in terms of event, this is or, right? Head, or head-tail. Is that okay? So, yeah, so this is an event. And one of the axiom of probability sort of requires that we be able to assign a value to probability of any event. So in other words, right, if we have probabilities for the outcomes like this, then we should be able to assign a value for the probability of events that are produced by taking the union or intersections of all the events, okay? So here, the rule would, I'm just kind of like telling you what to expect. The rule will be that it will be the sum, right, of the individual, right, outcomes that made up this event, okay? So anyway, the point is the assignment, right, has to be consistent in certain ways that we will go more in depth later on. The point right now, and the point I want to make, is that there's no unique rule to assign probability to outcomes. And so the most common assumption people make when they look at an experiment and look at all possible outcomes common assumption is that outcomes are equally likely. All right. Well, again, I mean, the assumption here has to come from somewhere. And the somewhere is that, like, basically, when you look at head, tail in this particular example, you don't see any difference in their likelihood. So you say that, yeah, they should be equally likely. In other words, right, the assumption really is that P head is equal to P tail head equals to P tail head tail equals to P tail tail. That is an assumption, or that is a model, let us say, right? Because again, are we sure that this is true in real life? Who knows? I mean, I guess the orthodox answer is you have to look at the data to verify, right, even that assumption. But that's my point, that right now we're doing probability, so we have some assumptions that we accept, and then we draw conclusions out of that assumption, out of those assumptions. So one of the common assumptions you encounter in basic probability and in this class is that outcomes are equally likely. In which case, right, we have this, and if you throw in, right, the sum, right, this one, the sum of the probability of the events has to be one of the outcomes, right? Then you will get that the conclusion that each of them has to be 1/4. Okay. So again, my point is that the assignment 1/4 here comes out of an assumption and comes out of some estimate of probability. All right. It doesn't come out naturally because so and so thinks so. No, right? Comes out of these assumptions. And then we can debate whether the assumption is right or wrong. And by the way, right, you will see that the conclusion that, let's say, the first toss is independent of the second toss will be a consequence of these assumptions. All right. So it's a logical consequence of the assumption that the outcomes are equally likely. In other words, I asked, right, is it possible to fill in other values for these outcomes? The answer is yes, but then the conclusion will be different. And I haven't checked, but possibly if you fill in other values, as long as they follow the estimate probability, the first toss will no longer be independent of the second toss. All right, possibly, I haven't checked. But so to conclude, right now I only have two messages for you. The first message is that probability is a way to assign likelihood to events following certain kind of axioms, following certain kind of rules, so that they're consistent and they kind of, follow, obey our intuition. And the second message is kind of along that line, that is, there's nothing natural, or there's nothing like has to be set in stone about certain kind of things we say. For example, that the first toss is in the second toss, or all this probability of the outcomes has to be 1/4. They all come out of the assumptions that we make about certain models. All right, so I think I've been saying a lot of things here, so I'm gonna pause and see if there's any question. All right, there's no question. Okay. So now, how does this tie back to combinatorics? Okay. Now again, I suppose that many of us here have seen some combinatorics. So I'll just say one or two words, and then of course we'll do combinatorics, in which we'll say more. But combinatorics basically is, in my opinion, right, rules for counting, okay, or ways to count quickly. For example, right, I just counted in this example. When I say we toss the coin twice, I say there are 4 possible outcomes, right? Of course, I think that's not too hard to come up with because you can list everything out. But the way I know it actually was not because I list all possible outcomes out, but because I do 2 times 2 is 4, right? For example, if you toss a coin 3 times, okay, maybe this is a place where we kind of throw in a quiz, right? So quiz 1, first question of the day. Suppose we toss a coin 3 times, okay? How many outcomes are there? Or, another word is, in other words, what's the size, right, of the sample space? Okay, what's the answer here? How many outcomes are there when we toss a coin 3 times?
8.
That's correct, right? So the answer is 8. And at this stage, I don't care how you come up with the answer. You can list everything out like this if you want. But obviously, you see, right? This is a slow way, very slow. And of course, if we do a coin, I don't know, 10 times, it's hopeless, right? To list all possible outcomes out. But 8, right, obviously comes out to be 2 times 2 times 2, or 2 cubed, right? So I'm saying this as a way to demonstrate maybe to some of you, because some of you may have already known this, that this is exactly combinatorics right here, right? This is the way to count quickly. Now, how does this tie into probability, or how does chapter 1, right, prepare you for chapter 2? I hope that, things are kind of obvious now, right? Because in this example, when you toss a coin 3 times, and you throw in the assumption that all outcomes are equally likely, right? Then exactly, you must know how many outcomes are there to write down this statement. For example, P hat is 1/8, right? Because if you don't know how many outcomes are there, then even though you know that the probability of each outcome must be 1 over the total number of outcomes, you have no idea what this number is, right? Something like that. So that's why combinatorics plays a crucial role, let's say, or plays an important role in probability, because it ties into sort of like counting when outcomes are equally likely. Which, right, also shows you that, well, if outcomes are not equally likely, then maybe combinatorics is not relevant, who knows? Or when outcomes are in a continuous mode, right, the continuous model, which we'll talk about later on in this course, so I won't really list them out here for you, then combinatorics are not relevant, but calculus will be. But anyway, right, so combinatorics is a very useful tool, a ubiquitous tool. So it's good to learn them anyway if you haven't learned them before. But in terms of probability, I just kind of want to give you the idea that it's a tool to study probability. Okay, combinatorics is not probability, but we study them to do work with discrete probability. Okay, that's sort of like where combinatorics is relevant. Okay. So having said that, we will now start chapter 1, do combinatorics. I think along the way, no, I don't think we'll be doing any probability in chapter 1, but, and then we'll go back to chapter 2 and, talk about probability more in depth when we're done with combinatorics. All right. Very good. Any question before we start chapter 1? Okay. So 1.1 is introduction to combinatorics, and I just want to say a few words about combinatorics. I mean, again, right? I assume that some of us here have seen combinatorics before. Like I said, right? It's basically a way to count quickly, or if you want, you can think of it like this. Basically, I don't want to make combinatorics sound easy. It's not, right? It's a very, very deep field, which I don't know much about. But as far as we're concerned, as far as the combinatorics we'll be using, I just want to kind of boil it down to this statement, which is really an oversimplification. It's basically a few rules that can be used for a lot of counting problems. Okay. Exactly how many? I think there are 3, but maybe there are more. So rules here can also be called principles. So basically what I'm trying to tell you is when you study combinatorics, at least at the elementary level that we're doing here, there are only a few rules you have to memorize, if you will. But then, right, the challenge is not about those rules. The challenge is to use them for counting problems where you combine them in the correct way to come up with the answer. And the challenge is exactly there, how to use these rules to do new problems. So the first rule we'll be encountering is 1.2, which is called the multiplication principle. All right. And I probably will just write down what the textbook writes and then discuss them with you. So the principle is like this. If our experiments are to be performed such that the first experiment, let me say maybe, yeah, the first experiment has N1 outcomes, the second has N2 outcomes, and you understand, right? Basically, then so on and so forth, right? The third has N3 outcomes, etc. Then there are N1 times N2, etc. times NR total possible outcomes. Okay. And you can see where the word multiplication comes from, right? Basically, if you have, the way I think of it is, R groups, right? And then each group has so many possible choices, and you take one choice in each group, then the total number of choices you can do is, number of choice here times number of choice there times number of choice there, blah, 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 right? Again, that's my language, or you can take this language however you want, right? In the end, I find from my experience that the challenge with combinatorics is to come up with the language and the image, right, that you're comfortable with. Everyone has somehow a little bit slightly different way to describe, the experiment or whatever they're counting. But people, when they know what they're counting, always say the same thing, more or less using similar languages. So, right, if things are unclear, whatever, feel free to ask. But I don't think there's like a single way, or single word to describe, the principle. Okay, but let's just give examples here, right? And we have seen, right, example in the previous examples, right? For example, if you toss a coin, let's say n times, right? Then how many possible outcomes are there? Well, clearly the n times here, the n here is the R there, right? That's n experiments. Now, how many outcomes are there in each experiment? Well, clearly there are 2 outcomes, right? In each toss, head or tail. Therefore, right, the total number of outcomes will be, right, 2 times 2 times 2, etc., right? How many times? N times, right? Which is 2 to the n, right? So this is a consequence, right, of the multiplication principle. I mean, you can also do something similar, but you toss a die, right, twice, right? Then there are 6 square, right, possible outcomes. Is that clear? Any question about this? Okay. So let's do another question, right? let's say a college committee consists of 3 freshmen, 4 sophomores, 5 juniors, 2 seniors. A subcommittee of 4 consisting of 1 person in each class is to be chosen. How many different subcommittees are possible? Okay. I think the answer should be quick here, right? What's the answer here? And by the way, right, answers of this type don't have to be a single number. You can write out as a expression. Like 6 square actually is a better answer here than 36. Is that okay? So what's the answer here?
Three times 4 times 5 times 2, 120.
That's correct. Yeah. I mean, we can stop here, right? I don't care what the final answer is. I mean, well, I don't care what the number is, right? This is good enough. Yeah, very good. Any question here? All right, so let's move on, right? So multiplication principle is pretty easy, I think. So now 1.3 permutations. All right. So maybe, right, let's just ask a question to demonstrate this. It's really a principle, but, right, how many ways can we permute the sequence A, B, C, D, E? All right. I mean, again, right, clearly A, B, C, D, E is just some choice. And what do we mean by permute, right? We mean, well, swap things around, right? For example, E, C, B, A, D is one permutation, right? D, E, C, B, A is another permutation, so on and so forth, right? The whole point is, right, you cannot, you know, use a element twice because, well, however many is there, you just swap them around. You cannot do any other, right, operation on it. How many ways can we do so?
Five factorial.
That's correct, right? The answer is 5 factorial. And what's the answer here? The answer actually is based on the multiplication principle, right? How so? Well, basically for any kind of permutation, right? Let's say you have permutation of n object. I mean, here, right, when we say n objects, it should be, right, by default that these objects are distinct. You will hear this word thrown around occasionally, right? What do we mean by distinct? Distinct is when, of course, A is different from B, different from C. The reason is once in a while, you probably will see something like this, right? And of course, if you swap D and D around, it results in the same sequence, okay? That's, let's say, a more advanced problem maybe. But when we say this, right, the objects are distinct, okay? Unless state otherwise. So that's not the case, right? So, but if you permute n objects, then the number of permutation, the total number of ways is n factorial ways, right? In which case here, there are 5 objects, so it's 5 factorial. But how does one come about with this principle? Well, if you have n objects, then clearly you have n positions, right? To put them around 1 to n, right? So these are positions. Think of them as slots, right? Like first slot, second slot, third slot, and so forth. Well, what do you do with the first slot? Well, you have to put something in, right? How many choices do you have there? We have n choices, right? Because you have n objects to put in the first slot, right? But whatever choice you put on into the first slot, when it comes to the second slot now, you will have n minus 1 choices, right? Because you already have one of them in the first slot. And right, of course, for the third slot, you have n minus 2 choices and so on and so forth until the last slot where it's kind of forced because it's the last object you have, right? And so now when you think with things like that, then you are back, right, to the setting of the multiplication, right, principle, where you have, right, n groups, each of them have so many choices. So, right, the total number of choices is n times n minus 1 times n minus 2, etc., which is exactly n factorial. Is that okay? Any question about this argument? All right. So let's see here. Now, of course, right, you will not be getting questions straight as a permutation or as a multiplication, but now you can combine them to answer questions. So let's say here's a question, right? There's 3, right? So the class consists of 4 sophomores and 6 sophomores and 4 juniors. The students are ranked according to the scores in an exam. No scores are the same. And you see, right, certain kind of words are thrown in to exactly, right, kind of give you that assumption that so here, right, when I say an object, these are distinct, right? And when they say no scores are the same, that's exactly to ensure that, right, the objects are distinct. You can distinguish the score of one student from the other, right? Okay, so the question is A, how many rankings are possible? And the answer here is
10 factorial.
that's correct. Thank you. Right. Now part B is that if the sophomores are ranked among themselves, same for the juniors, how many rankings are possible?
Is it 6 factorial times 4 factorial?
That's correct. Okay. So, any question here? So B, right, is an example of something like the permutation principle together, right, with the multiplication principle. But I encourage you to kind of, sometimes the language is kind of hard to parse, or it's a little bit weird to parse, because maybe you never encountered a situation where each group is ranked among themselves, so you may not even have any idea what they're talking about. So part of the challenge of combinatorics is really to think and to have a picture, right, of what exactly is the problem talking about. And once you have it, then it should be okay, right, to proceed with the tools to do it. Again, right, if something's unclear in terms of what the picture is saying, please ask, because I think we're still dealing with some kind of like easy question here. So if there's no one asks questions, we'll proceed. Is it okay? So 6 factorial, right, among the sophomores permutation, 4 factorial among the juniors, and then multiply them together, right? Because these are to make choice on each group using the multiplication principle. All right. So now some variation, right, of question B, you will see is, for example, if people have, I don't know, the typical question, I won't write them down, is basically block of, block of books, right? So for example, they say the physics books are to be kept together. The, you know what, maybe let's do this, right? Suppose you have physics, math, and let's say CS, right? Suppose you have 5 physics books, 4 math book, right? And let's say 8 CS books, okay? And here, right, the language can be, so I'm drawing a picture here so it can be a little misleading. So first of all, right, I'm just telling you, like, the way you count depends on the language you use. Suppose that you want to kind of like, let's say language is just to arrange the books, right, on the bookshelf or whatever, right? So that books of the same subjects are kept together, right? That's the language. That's it. And let's say that you have 5 physics books, 4 math, and 8 CS books. How many ways can you arrange the books on the bookshelf?
Would it be 3 factorial?
No. Now, actually, you're counting something that I expect people to miss. But 3 factorial, right, would be the way to arrange the groups. Oh, sorry. So, okay. I guess part of that is my fault, where maybe I have to tell you that the books within each group is different, right? So I guess that's sort of like in the assumption, but okay, it's my fault. So what we kind of mean without saying is that the physics books are not all the same books, right? Did you realize that when you do the counting?
No, I thought it
So-
was grouped together, that's why.
No, right, true. But do you see, even though they're grouped together, and then again, right? Maybe maybe I have to write down the question more carefully, or like this is a question from example 3C in the textbook. But no, it's fine, right? Basically, this is demonstrating that certain things, when you pose a question, how to say this? Okay, in combinatorics, that's why it's hard. For example, right? Okay, you say you think the books are kept together, which is true, right? Which is what the problem is saying here. However, right, you agree with me that the physics book can be permute among themselves and yet kept together.
Yeah,
So again, right, I'm just pointing out that exactly this is what combinatorics is tricky, because you may miscount when you overlook certain factors. But similarly, you may double count when you count certain factors twice, right? Things like that. Yeah. So that's correct, right? So basically 3 factorial for each of the subject among themselves, being permute. But then what you're missing is within each, right? There's this permutation of each books inside each group. So the final answer is something like this.
thank you.
Are we okay?
Mhm.
Yeah. Right. So actually, funny enough, I expect people to come up with this and miss the 3 factorial. You have the 3 factorial and you miss this, which is okay. All right. Any question here? All right, cool. So that's the first permutation principle. So now this is the second one. So that's the first principle, right? Let's call this the first principle. The second principle, I think they still call it the permutation, but I think it's usually referred to as permutation number. In some circle, you might see it like this as NPR. Out of N, choose R, but the number of objects are distinct, whatever. So let me tell you, right? So basically, let me write it down and I'll explain. So there are, oh, wait, hold on. Sorry, 1 second. This is not NPR. This is NC. Okay, let me not write out NPR. Let me just write this down. There are N factorial over N1 factorial, N2 factorial, etc. And sub R factorial, different permutations of N objects of which N1 are alike, N2 are alike, and R are alike. Sorry, this is not anything like NPR or whatever. Sorry, forget that. It's just the principle like this. Okay. So what is this describing? So for example, right, exactly similar to this one that I post, right? But now we allow the letters to repeat. For example, we have, let's say, AAA, BB, C, D, and then E. Okay, something like that. Now, so how many letters do we have total, right? So let's clarify, right? What's N1? What do we mean by N1 here? N1 is 3, right? The number of letters in the first group. So N1 are alike, right? N2 is 2, N3 is 4, N4 is 1, and 5 is 5. Is that okay? So N in total, N here, right, is the number of total objects will be 3 plus 2 plus 4 plus 1 plus 5, which is 15. Okay. Now, you can still, right, permute this together among each other, meaning you can swap them around. But like I explained, right, when you swap, let's say this E and that E, or you swap this E with that E, nothing will happen, right? It will still be the same sequence. Therefore, when you have repeating, right, I like to say this as repeating, right, objects, or you can just use the book's language, whatever, then the number of distinct ways, right, that you can swap things around will be this number. In this case, right, it will be 15 factorial over 3 factorial times 2 factorial times 4 factorial times 1 factorial times 5 factorial. Any question about this principle? Okay, so that's one example, right, where this shows up. But here's another one. So let's say this is quiz 4. Oh, sorry. Okay, let me do this and then I'll explain where this comes from, right? Where this principle comes from. So I guess you see this when people have only color flags without any picture, right? So how many different signals consisting of 9 flags hung in a line from a set of 4 white flags, 3 red, 2 blue, where flags of the same color are identical.
Nine factorial over 4 factorial, 3 factorial, 2 factorial.
That's correct, right? Yep. So again, right, this is just a straightforward implementation, right, of that formula. Now, so does someone want to explain? Let's see if you understand this. Where does this formula come from? Why would the formula come out this way? Like, for example, right, in this problem of the flags, right, why would it come out to be this 9 factorial over so and so?
Is it because the colors are identical, so it doesn't make a difference?
True, but no, yes, but when you explain, I guess, formula, right? I
Mhm.
guess you want to kind of string them together in the sense that like you want to use the original formula, let's say, right? For example, right, the permutation principle is built out of the multiplication principle, right? And then when we do this kind of blocks of books, we also build out of the permutation principle and the multiplication principle. Does it make sense? So
Mhm.
I'm asking if anyone can explain, in particular, right, why the division, for example. So far, we haven't done any formula that has division, right? Can we explain where that comes from?
Would it be because n factorial is like the amount of total positions and you must divide it by like the sub positions within each color? If that makes sense?
That makes perfect sense, and that's exactly right the reason. So exactly right. So when you look at, for example, right, let's look at this to make it more concrete. The 9 flags, if they're all different, right? 9 flags, right? If they're all different, then there are 9 factorial permutations possible, right? If all different. Okay, so that explains the 9 factorial. On the other hand, right, what is this number? 4 factorial times 3 factorial times 2 factorial. What is this number? This is the number of ways, right, that you can permute within each group, right? This is exactly the same number that we will come up with if we, right, look at the block of books like this, only permuting within each group, right, but keeping the order of the books the same way. Does it make sense? So, right, when we do 4 factorial times 3 factorial times 2 factorial, that's the number of ways where you keep the group together, right? When you keep the white flags together, or the red flags together, the blue flags together, and then just permute within each group, right? The number of permutations, right? When we keep the flags of the same color together. Is that okay? And so now you think about this, right? Basically, out of all possible way to permute the flags, right? What can you do? You can permute the flags in such a way that flags of the same color are kept together, or, right, you can permute them in other ways. But notice, right, because flags of the same color cannot be distinguished, right? So basically what I'm saying is there is a multiplication principle going on here. You have the number of ways, number of permutations, where you keep the flags of the same color together, and then multiply, right, with the way, with, let's say, an x, right, which is exactly the number of the other ways, right, to permute the flags. Together, this will give you the total number of ways to permute the flags, right? Now, these are the number of permutations that will not be seen because the flags of the same color are identical. So this is the way of permutations, the remaining ways where, right, the permutation can be distinguished. Therefore, x here will be 9 factorial over 4 factorial, 3 factorial, 2 factorial, like that, right? So basically what I'm trying to tell you here is it's like sort of like the reverse, right? The opposite of the multiplication principle, right? If you use the multiplication principle, then you can come up with the total number of permutation. But what you're trying to solve for here is the number of permutations left when you, let's say, factor out or mod out the number of permutations that cannot be seen because the one with the same within the same group are identical. Does that make sense?
Yeah.
Okay, good. So again, right? I mean, it's not super. Well, okay. I don't know if it's important or not. I do think, right? I'm not trying to over-explain certain things here. I think it's important for you to understand where a formula comes from. The reason is this, right? When you have to string these formulas together for a complex problem, you cannot just like throw formulas into the air and hope that they come together correctly. It will never happen that way. You get the right formula because you understand how the formula works, how the pieces fit together. This is why I'm trying to explain this, right? So that you have an intuition, right? Okay, cool. So now, let's see what time it is. Okay. So now we're done with the permutation chapter. Let's go to 1.4, permutation section. This is called combinations. And actually, the combination here will be very similar to this principle. With two groups. Okay. So let me say this. Just definition. Or let's say this, right? Let's say this is a principle. The number of ways to choose or select k objects out of n objects. And usually there's a word here that's a favorite word where order does not matter. Okay. It's gonna be denoted as n choose k. So it's a big parenthesis, right, on both sides, n on top, k at the bottom. Some people write NCR, NCK. I think I've seen this, but it's not common as far as I know. In my circle, people write N choose K like this more, right? I'm just saying this so you might have recognized this if you've seen it before. N choose K, right? So pronounced as N choose K. Okay. And here, of course, right, K is less than or equal to N. We're gonna go 0. For obvious reason, you cannot select more than n objects out of n objects. You cannot select a negative number of objects, right? And the answer here will be n factorial over k factorial and n minus k factorial. Okay. So let us demonstrate, right, what this principle means, and then discuss where it comes from, etc. By far, I think this number is, well, of course, with this permutation as well, the number of ways to permute things, like this one. By far, these are the two most commonly used principle in basic probability, as far as I'm concerned, or as far as my experience goes. But well, let's see what example can we have to state this, right? So, for example, let's say, suppose we select. You know what? Let's just say this, right? This is actually from the binomial theorem. And maybe let me make that into a question. So this is question number 5. Suppose I have x plus y raised to the 10th power, right? Now, using expansion, right? It'll be x to the 10, and then so on and so forth, right? With y to the 10th, right? At the end. In between, right? I'll have certain things where, let's say I have x to the 4th, right? Y to the 6th, right? And, x to the 5, y to the 5, etc., right? So the question is, how many terms are there, or what's the coefficient in front of, let's say, x to the k and y to the 10 minus k, right? For 0 less than or equal to k less than or equal to 10. Is that question clear? Right? When I expand this expression, right, I'll have terms where the powers, right, always add up to 10, correct? But then, right, there are coefficients in front of these terms. Well, I mean, let me give you an example, right? I mean, you should know this, right? X plus y squared is x squared plus 2xy plus y squared, right? Everyone knows that. X plus y cubed is x cubed plus 3xy squared plus 3x square y plus y cubed, right? Things like that. So now I'm asking for the 10th power, let's say, right? What are the coefficients in front of each expression, each term? And more importantly, right, can you explain why that is the answer? Okay, what's the answer?
Ten factorial over k factorial, 10 minus k factorial.
Correct, right? Or, in our line of business, you can just say 10 choose k and people would understand, right? Because when you say 10 choose k, people would know this formula. Yeah, that's correct. Okay. Now, so first of all, right, let's try to see that this is true for this one, right? First of all, right, you see that the coefficient like x to the 10, y to the 10, right? They're 1 and 1. What do they represent? They represent 10 choose 0 and 10 choose 10, right? Let's say. And clearly they're both 1. In other words, right, n choose 0 equals to n choose n equals to 1. Now, of course, you can do the math, right, and check out that this is exactly 1, but it's not that illuminating. Let's try to understand to see if it's true together with the description and principle. Like, how many ways can we choose 0 object out of n objects? One way, right? Choose nothing. How many ways can we choose n objects out of n objects? One way, right? Take them all. Is that okay? So that's, at least it's correct according to our intuition, right? So what I'm trying to say is this principle here can be understood intuitively, right? You just don't have to rely on the formula. Now, secondly, right? For example, what is 2 here? 2 here represents 2 choose 1, right? 3 here represents 3 choose 1, and 3 here represents 3 choose 2. Okay. And you can check, right, that 3 choose 1 is 3, 3 choose 2 is 3, according to this formula. Now, so in general, so can we explain, right, why is so this is called a binomial coefficient, right? Why must it be, right? For example, right? So what we're saying, let me reduce it down to 5, right, to be able to write down easily for you. For example, this is x to the 5, and then 5 choose 1, x to the 4th, y, 5 choose 2, x cubed, y squared, 5 choose 3, x squared, y cubed, 5 choose 4, x, y to the 4th, and then you can do 5 choose 5 here, just 1, y to the 5th, something like that. Okay. So yeah, can we explain why it must be something like that, right? So in general, it's n choose k if it's x plus y raised to n power, or the k power term, right? Why is that so?
Can you repeat that question?
Oh, I'm just asking, right? So your friend say, right, that the answer to the coefficient in front of, right, these terms is n choose k. You see? So for example, here, I guess the 1 here corresponds to power y, right? 1, 2, 3, 4, right? I'm asking why is that true, or why must it be the answer? I mean, I want you to be able to connect, right, the development of this formula with the principle of the combinatorics.
Is it because? Oh, go ahead.
Is it if you like write out x plus y, like times itself 5 times, then you're like basically choosing either an x or y from each one when you multiply. So, for example,
Excellent.
like
No, that's exactly it, right? So I want you to be able to see that exactly is an act of choosing, right? So right, exactly. So when you do this, essentially you have 5 groups, right? And say if you want, let's say x cubed y squared, what does that mean? That means that you have to select x from 3 groups and then y coming from the other remaining 2 groups, right? That's it. And now, does order matter here? The answer is no, because x from these 3 groups will always result in x cubed. Doesn't matter if you choose this group first, this group second, this group third, etc. Right? So that's why these 2 together, right? That you choose x from 3 groups, y from the remaining 2 groups, results in, x cubed y squared, and hence, right, the 5 choose 2. Is that okay? And so, right, actually, what principle did we just talk about? We kind of referring to the fact that n choose k would be equal to n choose n minus k. Do we see? I mean, of course, you can check that the formula tells you so, right? But again, right, I would much prefer that we see it from the choosing intuition, right? Why? Because, if you have n objects, right, and then you have 2 groups, that's what happens, right? One of the group you put k objects in, then automatically what happens? You have n minus k objects left, right, in the other group. So basically, when you choose k in, it's almost like you choose n minus k to left out. I mean, actually, it's not even almost, it's exactly the same, right? So these are equal. Okay. What else do I want to tell you? I thought of something I forgot. When it comes up, I'll tell you. So now, maybe let's try to explain, right, where this number comes from. Okay. So I hope you recognize, right, that this structure is very similar, right, to the structure of principle number 2 in the permutation, right? However, I guess the flavor is slightly different. So it's actually exactly this formula when R equals to 2. When R equals to 2, that's exactly the combination number is exactly the principle number 2 over there. So the explanation is still the same, right? So basically, it's this, that when you divide, right, n objects into 2 groups, right, well, you don't care how the groups are ordered among each other, then there are k factorial ways, right, for the first group to order among themselves. There are n minus k factorial ways for the second group to order among themselves. Now, of course, right, when you multiply these numbers together, there's still a mysterious number left, right, for how you can select things into the first group or how to select things in the second group, so that in total, that will result in a total number of permutation, right? So that x right here is exactly the combination numbers. Is that clear? So in other words, right, you can think of the number of ways to divide, right, an object into 2 groups as follow. There's a number of ways for you to choose k objects from n objects, right? You put in the first group. That automatically leaves the remaining objects in the second group. But if you try to permute this among each other, then there's k factorial ways to permute among the first group. There's n minus k factorial ways to permute among the second group. And if you string all of those ways together, that's exactly the same as the total number of ways you can permute n objects. Therefore, right, when you solve for x, you can divide and get the combination number. Are we clear on this? All right. So let me just write down the binomial theorem in a more formal abstract way, right? So the binomial theorem is x plus y raised to n power is, right, obviously x to the n plus n choose 1, x to n minus 1, y, n choose 2, x to n minus 2, y square, etc., right? N choose n minus 1, x, y to n minus 1, plus y to the n. And people usually write like this, right? The sum k equals 0 to n choose k, x to the k, y to the n minus k. Or the other way around, right? X to the n minus k, y to the k, doesn't matter. It's symmetric. So, right, this is a condensed version of this. All right, any question? All right, so I think here the textbook does not mention the permutation number, but let me just mention it just in case, because I think in some context this happens. So I think, right, it's called permutation number, but let me just write it down without naming it. So basically it's this. The number of ways to select k objects out of n objects where order matters is k factorial times n choose k. And of course, if you write down, right, it'll be k factorial, n factorial, n minus k factorial, k factorial. So these two cancel each other out to give you n factorial over n minus k factorial. Right. So I believe, right, this is called NPK, but check me on this, okay? This is called a permutation number, but I'll explain the context. So first of all, right, for me, this is much more understandable than remembering this formula. So I always remember the combination number, and then I just modify it to suit the situation. So here's an example. I'm not sure if it's the best example, but just try to demonstrate. For example, if you have numbers 1 to 10, right? And suppose that you want to select, let's say, 4 numbers, right, out of 10. But then when you select the 4 numbers, you will rank them. Oh, sorry, not rank, but when you want to permute these 4 numbers among each other. And let's say where order matters. Okay, so what does this mean? So for example, let's say I select 1, 4, 5, and 6, right, as a group. So I select 4 numbers, right? But if I do combination, then this is the same as 5, 4, 1, and 6. Does that make sense? In other words, right, this is the same as this if I count them under combination. However, if I count them under permutation, or when I say order matters, so this is order does not matter. Then these two count as different ways. So order matters. Okay. Now, this may make you confused, and it might as well be, but that's just the way things work. Sometimes you count under this way, sometimes you count under that way. Now, can I tell you which is which? Sometimes the word order matters will come up explicitly. People will tell you order matters or order doesn't matter. But a lot of times it's not that explicit, and you have to distinguish the context. Let me give you an example that I can think of in this case where these two are distinguished. For example, right, you can have 10 numbers in the back, let's say, and you put your hand in, and then you grab all 4 at the same time, and you just look at what they are. Does it make sense? So it's like you have a bag of 10 numbers, and then you put your hand in and you grab 4 out, and you see what they are. That's all. On the other hand, right, this may describe the action of you put your hand in 1 at a time and select each number out, and you care to record the sequence that you draw the number out. Does it make sense? In that way, because you care to record the order of that, how it comes out, order matters. Of course, you can still pull things out 1 at a time, but then you don't record anything. You just see what objects come out in total. Then it's combination. Does that make sense? So all in all, I just want to tell you that these things is context dependent, and a lot of times it's a little bit vague. So you have to really pay attention to your context and see what the problem is trying to tell you. Right? That's the best I can put, right? So 2 things. Are objects distinct or objects identical? That's one source of confusion. The second source of confusion is, does order matter or does order not matter? All right. And being able to distinguish this, I think, is one of the important ways, right, for you to navigate at least basic combinatorics problem. All right, any question? All right, so let us move to 1.5. Multinomial coefficients. So we're moving quickly now to cover all the principle. If we don't have time today, we're gonna do a lot of problems, okay, on Wednesday to demonstrate this principle more. Right now, at least with this principles, I feel like we cannot do problems until we cover all principles, at least, you know, discussing them a little bit, because who knows what we'll be using when we solve problems. All right, so the multinomial coefficients. So by the way, right, this n choose k here, right, is also referred to as the binomial coefficient, right? And for obvious reason, because, you know, it's attached to the binomial theorem, right? It comes in front of the binomial, the coefficient of the binomial expansion. But, you know, people refer to it by different name, right? N choose k, binomial coefficient, blah, blah, blah. It's the same object. So the multinomial coefficient should not be a surprise. It's the number of ways, right, to choose or to put, right? Let me just say to choose, right? N1, N2, etc., Nr objects, right? Among, or let's say, to put in to R groups, right? So basically, it's a generalization, right, of the binomial coefficient, but the binomial coefficient is number of choose N1 objects to put to a first group. The reason, right, is because, okay, let me just write down and then, so it will be written as N, choose N1, N2, etc., Nr, which will be N factorial over N1 factorial, N2 factorial, etc., Nr factorial. This is multiplied together, where N1 plus N2, etc., plus N sub R is equal to N. So, right, again, so basically the N is the total number of objects you have. You have R groups that you try to divide these objects into, where the first group has so many objects, right? A second group has so many objects. And here again, right, of course, the order does not matter among each group, right? And so when R equals to 2, you should receive that it reduces to the binomial coefficient, right? Because N choose N1, and because N1 plus N2 must be equals to N, then it clearly is just N minus N1, right? And of course, the formula says it's N factorial over N1 factorial, N minus N1 factorial, which is just N choose K, right? Where K equals to N1. So the multinomial coefficient is a generalization, right, of the binomial coefficient. Now, for example, right, let's see. And it just gets like kind of big when we write things down. But suppose you write x plus y plus z to a fourth, let's say, right? then what do we have? Well, we of course have x to a fourth, right? First of all, and you have y to a fourth, and you have z to a fourth, right? But somewhere along the way, you will have something like x, y squared, and then z, for example, right, as a term. So, you know what? Let me even bump it up to the sixth power to, you know, have more interesting, right, combination. So let's say for 6, let's say I have x cubed, y squared, and z. So what do you think, right? What coefficient comes in front of this term? It will be 6, choose 3, 2, and 1, right? Which really will be 6 factorial over 3 factorial, 2 factorial, 1 factorial. And then of course, right, we have other combinations such as x to a fourth, y squared without z, right? In which case it will be 6, choose 4, 2, and 0. And so on and so forth, right? Are we okay? Now, what I want to draw your attention to is, right, this number is exactly the same number as the number in this second principle. Okay? However, right, the description is slightly different. Here, the context is that you have objects that are alike, and then you try to permute them among each other and count the number of different permutations. The multinomial coefficient is about putting objects into a bag, let's say, right? You try to put 3 objects into a first bag, 2 objects into a second bag, etc. But when you think about it, right, even though the description is slightly different, the way you operate is the same thing. In other words, right, you still, because objects in the same bags are counted in this, are not counted, then in the end, right, what you have is the number of ways you permute objects in the first bag, the number of ways you permute the object in the second bag, etc., right? And the number of objects, the ways you permute object in the last bag. All of these are not counted, times the number of ways you select, right, objects into each bag. This together should give you the total number of permutation. And so when you divide, you get the multinomial coefficient, right? So that's another, thing about combinatorics at work for you. That is, you can have slightly different description. The formula comes out the same. Well, the reason is you end up doing the same thing under these 2 descriptions. All right, any question? All right, so I think we have 10 minutes and I'm gonna pick just problems, let's say randomly from the end of the chapter 1. So there is section 1.6, which is, the number of ways to partition a sum, which I'll skip for now. If somehow that subject becomes important, because this class is not a class about combinatorics, it's a class about probability. Like I said, we study enough combinatorics to serve, right, the purpose of probability. So partition, I don't think is a topic that would come up a lot in the kind of probability we'll be doing. So I'll skip them for now. If we need it, right, we'll go back and cover that section. So for the last 10 minutes or so, I want to do some, further problems with you. So let's say this is quiz 6. Let's say this is question number 17, okay, in chapter 1. It says this: a dance consists of 22 students, of which 12 are men, 10 are women. If 5 men and 5 women are to be chosen and paired off, how many selections are possible? What's the answer here?
Choose 5 and times 10 choose 5.
That's correct. Any question here?
Doesn't this
So
like
next. Yeah, go ahead.
you can
What's your
go
question?
first. Doesn't this like are we considering that, like, say let's just say we numbered the men and women. Is it saying
Uh-huh.
that we're pairing, like, if we choose like 1, 2, 3, 4, 5 men, for the
Uh-huh.
first 5 men and the first 5 women,
Uh-huh.
and we pair them up, then it would be 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5. But isn't like 2 to 1, 1 to 2, 3 to 3, 4 to 4, 5 to 5 a different pairing?
Yeah.
In
So
which
that
case,
exactly is accounted in here, right?
so wouldn't order
Because
matter? Which so it'd be permutation MP 12P 5?
no. So you see, that's exactly where confusion happens, because we mix a lot of principles together, right? Here's the thing. So you have a group of men, right, in which 12 of them are there, 10, right, in which women are there, right? So first of all, out of 12, you choose 5, right? 5 men. Now, does order matter among this choice of 5 men? Right now, the answer is no, because you're not pairing them up with the women. Agree? And also, out of the women, you choose 5. All right, and let's say you go with your example, the first 5 male, the first 5 female, right? But then you propose that one matched with 1 is different from one matching with 2, which is perfectly valid. But is that about order being matter? The answer is no. That's the multiplication principle at work, right? You have 5 choices here, you have 5 choices there. How many choices can you string together among the two groups? Does that make sense?
So I have a quick question.
Say,
If it said
yeah.
that, sorry, if it said that order did matter, then would you be saying, if it said that order
Well,
did matter,
but order would, it's hard to imagine what order matters here
in this
mean.
situation? Yeah,
Correct, unless you're talking about like they dance in different orders or something, right?
'Cause,
Like they dance the first song, but right now they're
Yeah.
just pairing off. You
Right.
So yes,
Right.
but then the description would be must be more complex and there must be another element introduced so that order
Okay.
starts to show up. Does that make sense? But I think
Yeah.
your friend's point is that he, to the best of my guess, he's confusing, well, not to his fault, the multiplication principle with the order matters thing, right? That's what I'm trying to explain.
Yeah, I had a separate question from it.
No,
Um,
I understand your
oh.
question as well.
Oh,
But that
okay,
would
got it,
have
got
to
it,
be for further description. Yeah. Right now, I think there's
If-
nothing to. Yeah, go ahead.
So if like if we have because we're choosing 5 men and 5 women from the 12 and 10 men and women respectively, if we're choosing 5 men and if like the order did matter, so like if we did like the first 5 women or first 5 men into like a 12 numbered men, and then if we reverse that and then chose 5, 4, 3, 2, 1, and then those would be counted as different sets, would it just be the same thing as like k time or like the k factorial times
Mm,
then choose k?
so no. So okay, here I can see what's at work
Yeah.
here in both of your questions is that you are, I guess, again, I'd say for lack of better words, you are sort of like confusing the order here and what has been done within which. So here, right? I guess the listing is excellent in the sense that okay, if you have 1, 2, 3, 4, 5, and let's say, right, let's do the order as Roman numeral to distinguish them, right? So one is the first group, one is the second group. Agree? Now, if my question is how many ways can I match one element from each group, what's the answer? 5 square, right? Agree?
Yeah.
Because, right. But notice 5 square already consists of what? 1 matching with 2 and 1 matching with 1 and 1 matching with 3. You see what I'm trying to say? So in other words, right, as long as you have these guys ready to go, then they will be matched with all elements in the second group. And I think that's what you are thinking of when you say order. You know what I'm trying to say? When we say selection, when order matters, we're talking about the act of selection itself. We're not talking about the matching between the two groups.
Yeah.
Does that make sense?
That yeah, I was talking about when you're selecting 5 men from the group of 12 men. When you're
Mhm.
selecting so if it's ordered and your 12 men in the like group of 10 or 12 men are numbered 1, 2, 3, 4, 5, 6 all the way till 12, and you're choosing 5 men from that group of 12 men, and then say you choose in one selection you choose 1, 2, 3, 4, 5, and then you choose 5, 4, 3, 2, 1. Though that's what I'm saying. Would there be a difference between saying 1, 2, 3, 4, 5 is the same thing as 5, 4, 3, 2, 1 versus they're different and they
Okay,
don't
so
count
what
and they
no,
don't
no, but what
equate.
what I'm trying to explain to you is to answer a question, you have to imagine what you're doing, right? Because your purpose, according to this problem, is to match this men with the ladies. Do you agree? That's all you're trying to do, right? You're matching them
Yeah.
together. Does that make sense? So in the end, you count the different pairs. Do you agree? That's the language of this problem. Do you agree?
Yeah.
And so in that sense, can you imagine if we reverse the order of selection of the men and we pair them up? Do we do anything differently?
No, it's still accounted for.
Right, because we care about the pair. Do you see? We don't care if we pair this guy with this lady first, whatever. So I understand where the confusion comes from, but I would like to say that the confusion comes from a little bit dogmatic worry that somehow order might matter here, and not looking into the end result of the problem, which is pairing these ladies and the men together, right? If you really look into that part, you will see that why do I care about which order I select the men first or second? Do you see what I'm trying to say?
Yeah, so because you're pairing the people together,
You're just
it
pairing
doesn't
them off,
matter
right?
if
You're
you
just pairing them off.
right.
Correct. So that's exactly, and then your confusion, which I completely sympathize with, is exactly the difficulty with combinatorics problem. Like you really have to understand what they're trying to accomplish here, right? And then usually the problem it doesn't speak to you to clarify, but you have to interpret it to the best. But like here I say, right, you probably can read it if you imagine what's going on, and yeah. Anyway, right? Yeah. No, good question, and demonstrates this. So I plan to have the second question, but no, we don't have time. So I think it's a good place to stop here, and we'll continue, right, with more problems, as you know, combinatorics, for the next class. All right. So for now, I'll stop here. A set of problems will be posted, okay? And then, like I said, problems will assign every lecture, and will be collected. The whole week will be collected by next Monday, right? By the following Monday. So I don't want to collect questions every lectures because I will rush you, but that doesn't mean that you want to wait until the weekend to do all the problems, because you'll be doing problems from 3 lectures for homework, right? Okay. So just watch out for that. If not, I'll see you on Wednesday. Have a good day, and if you have any questions, I'll be happy to answer.
Thank you.
Sure.
Thank you. Have a good day.
You too.
Hello, Professor.
Yeah.
Just a thing before we go. Did you see my email about my conflict with the first midterm timing?
No. When did you send them? Right before class?
I sent it last Friday, I believe. When
Are you sure?
it should have, yeah. I can explain it right now if you have a bit of time.
Go ahead. Yeah. Well,
Um,
let me stop recording because that's not doing anything.
Okay.